Good morning. Here is what we are going to do for the rest of the week. Today we're going to finish 3.2. Tomorrow there's no school, but I'm going to give you some practice problems to work on because on Wednesday we're going to do homework corrections for all of 3.2 because I don't think we've had a single homework correction for this whole section. So we'll do a big homework correction on Wednesday, and then Thursday we'll do a review video, and then Friday you have your 3.2 quiz, and then next week we will have kind of a short-ish week. We'll just review on Monday and Tuesday, and then on Wednesday you'll have your Unit 3 exam covering 3.1 and 3.2. And then on Friday you graduate, as long as you pass all these things. No, I'm joking, but kind of. Okay, so we are going to do 3.2 today, finish her off. So let's start with that. So 3.2 we're on, I think you did F and G. You did notes on F and G. And I wanted you to actually read them both together because it's kind of pointless to talk about them separately. We're just going to go over them combined. So we have 3 types of projectile problems that we can get all sorts of information from, and we can deal with these problems differently based on the type of initial information we're given and we're provided. So what we're going to do is I'm going to basically give you... we're going to talk about the 3 types briefly, and then I'm going to give you the equations for each of the 3 types, and then we're going to do some practice problems, and I'm going to give you kind of a problem-solving strategy to help you solve these questions or solve these problems when you see them. Okay, so the 3 main types. First, we have dropped projectiles, which aren't really... they follow the same patterns as the other 2 types of projectiles we're going to talk about, but we already did this. Do you remember when we were talking about dropped objects? We have two types. We have dropped, or we have thrown. And remember, we did this in, I think, the first unit. We did this a long time ago. So we're not going to really focus on dropped projectiles, but you do need to know that there are 2 types of these quote-unquote dropped projectiles, and those are projectiles where if I'm standing here, something drops straight down. So it has no initial horizontal velocity, and it has no initial vertical velocity if it's dropped. Dropped has no... Let's erase this. No initial VIX or VIY, right? So if I were to draw this, I guess I just did have it drawn. It would, let's do it this way. We're standing on this, so it would just go straight down. This is as opposed to the other projectiles that we've seen where we have some horizontal velocity or an upward projectile where we throw it up and then it falls down like this, right? So we have these 3 different types of projectiles. So we have dropped, which has no initial VIX or VIY, or initial, that's redundant. But so the equation for this that we're used to, we've already seen, is 1/2 GT squared. So the y, the vertical distance that it falls, is just 1/2 GT squared. And then if we have a thrown object, that means we are throwing it down. We're not just dropping it from a roof. We're throwing it with a force down. So this does have VIY, but still no VIX. Still no horizontal initial velocity because it's just going straight down. And if we have this one, we already know that to find the distance that it falls, which is y, we would do VT plus 1/2 GT squared. Where V, since we have only vertical velocity, since we're throwing it, obviously that's got to be vertical. It's not horizontal velocity because we don't have a horizontal velocity. So you need to understand this. You need to be able to solve these problems. However, I'm only gonna focus on explaining the 2nd and 3rd type of projectiles today, in general, because we've already done dropped stuff a million times before. Our horizontally launched projectiles. So there were some equations. Our second are these, and our third, I'm just going to lay these out first, are our upward or our angled projectiles. All right. So that's, if we're standing here, our horizontal projectiles would be the ones thrown, and that looks more like it's up, doesn't it? They're thrown straight out with an initial horizontal velocity, but with no initial vertical velocity. And an upward or angled projectile is thrown up with an initial horizontal and vertical velocity. Okay? So before I get more into this, I want to go back to when we were doing our kinematic equations. We had several different kinematic equations, right? We had, I'm just going to write them all up here. All right, so we had these, we had way more than this, but these were the three common ones that we used over and over and over again. And these were used for motion in one dimension, right? We haven't done motion in two dimensions until now. So we can actually use these kinematic equations to describe the horizontal motion and the vertical motion. But we're going to have two distinct sets of equations because our horizontal motion and our vertical motion are independent of one another. So let's do our horizontal first. So for horizontal motion, so instead of d here, I'll have x. And I'll have Vix times t ax. And I'm going to change all of these basically to just add the x to let you know that I'm looking at my horizontal components of motion and not my vertical. So if I continue here, I have Vf, my final horizontal velocity, my initial horizontal velocity, and then I have that, and I'll erase the d here and replace it with an x. Okay, so let's go through and say what each one of these are. So we have already seen this. This is horizontal displacement. Horizontal displacement. This is initial horizontal velocity. T is time. A is the same thing. This is acceleration. This is horizontal acceleration. And we're going to see when we talk about vertical acceleration that A is actually G, but we're not going to get there yet. So VF, that's the only other one. This is going to be the final horizontal velocity. And then I think I've got them all there. Okay, so we have to narrow this down a bit, though. We don't have to know all of these equations because the first thing that you should think when I tell you this is horizontal acceleration, it's that with all of our projectiles, do you remember the force? What is the only force acting on the projectile? The only force acting on any projectile is the force of gravity. You should also remember that in order to have acceleration, there has to be a force, right? So there's only a vertical force. The force of gravity is not a horizontal force. The force of gravity has nothing at all to do with the horizontal motion of the object. It does not influence the horizontal motion of the object. So that means that the acceleration for any projectile, the horizontal acceleration for any projectile is 0 meters per second. Because if there was an acceleration horizontally, then there would have to be a force horizontally. But there's not a force horizontally. There are no horizontal forces acting on a projectile. Only the force of gravity, which is a vertical force, pulling it straight down. Therefore, every place we see this AX here, this is a 0. If I have 1/2 times 0 times t squared, this whole term right here becomes 0. So this all gets erased. That whole thing is erased. Goodbye. Because acceleration is 0. All right, so now I'm just left with this equation, which, if you remember, is an equation we've already seen before, minus the plus sign. We've seen this equation. Every time we talk about how to determine the horizontal displacement of an object, we talk about this equation. All right, let's look at the next equation. Vf(x) equals Vix plus, oh, there's acceleration again, so this whole term becomes 0, because 0 times anything is 0. So we can erase this whole term. If we look at the last one, same thing. We have another ax here, so this whole term becomes 0, so we can erase this whole term. So what we're left with, really, is only one equation that's useful, and this is more of a statement, right? So this says that because if we let's look at it, I'm going to stand on this building and I'm going to throw an object straight out and it's going to fall to the ground, and I'm going to look only at its horizontal motion. So I throw the ball with an initial, that is a really thick pen, with an initial horizontal velocity. My Vix is equal to 20 meters per second. When we're not even going to look at the vertical velocity, vertical motion, nothing about the vertical components of motion, because when we talk about this stuff, we can talk about the horizontal components of motion as if they're without any discussion of the vertical, because they're completely independent of one another. So at t equals 0.00001, as soon as I throw the ball, this is my initial horizontal velocity. At t equals 1 second, what is my, or 0.1 second, whatever the time intervals are, what is my horizontal velocity? What is just Vx? It's going to be 20 meters per second. Why? Because there's no acceleration. Well, let's say there's no force acting here, right? There's only a force acting down, but that force does not influence the horizontal motion. So there's no force. If there's no force, that means there's no acceleration. If there's no acceleration, that means that velocity is constant. So that means throughout this whole entire path here at t equals 2, my velocity equals 20 meters per second. At t equals 3, the horizontal velocity is 20 meters per second. You get the picture. All of these are 20 meters per second, 20 meters per second, 20 meters per second, 20 meters per second. So when it stops, when the final Vfx is also equal to 20 meters per second, which is beautiful because that's what our equation says. But so this equation is basically just telling us something we already know. It's not really a useful equation. And the same thing with this one down here. We're not going to use either of these equations. The only equation we're ever going to use is this one. But it's important to understand how we derive these equations and why. You need to understand this for your exam, or for your quiz, not for the exam. Well, maybe for the exam. I haven't decided yet. You need to understand how we take these kinematic equations, well, it was not these kinematic, it was these. Let's paste them here. How we took these kinematic equations and we turned them into basically just this useful equation for determining the horizontal components of motion. So we took all of these and we have compiled it into just this one for the horizontal components of motion of a projectile. Now let's look at the horizontal components of motion, the kinetic equations for those. All right, so let's look here now at the vertical components. So here are my 3 kinetic equations that I've seen before. But now I'm going to replace my d displacement there with y, which is vertical displacement. And then I have VIY, I have AY, I'm going to change the VFY, VIY, AY, VFY squared, VIY squared, to, let's erase the D there, get rid of this D, write a little y, and then a big Y. Okay, so again, so we have vertical displacement, which is y. We already know that. This is not new information. We've been using an equation using y several times, well, this whole unit or chapter. Then we have the initial vertical velocity times time plus 1/2 ayt squared. This ay is the acceleration, the vertical acceleration. Vertical acceleration of a projectile is also known as g. So we've seen this equation before. I'm going to say that again. The vertical acceleration of a projectile, or ay, is equal to g. Equals g, which is equal to 9.8 meters per second squared, right? Okay, just so you know, this isn't a new crazy equation. Don't freak out. You're not getting a bunch of new equations. This is an equation you've seen before. All right. And then here we have the final initial velocity is equal to the initial velocity. The final vertical velocity is equal to the initial vertical velocity plus ay, which is also g, times t. And then finally we have the final vertical velocity squared is equal to the initial vertical velocity squared plus 2ay, which is g, times y, which is vertical displacement. Okay, so those are the three equations that you're going to need to use that we're going to let's wait. We're only talking this. So these are the three equations that we're going to use when we're talking about horizontally launched projectiles and angled upward projectiles. So first, let's look at the equations that we need for horizontally launched projectiles. So we already know that this is going to be the only one we use because we're not going to use any of these others. This is not even an equation. These are just statements, basically. So we have x. All right, there is for our horizontal component of motion. This is the equation that we will use when we want to figure out anything having to do with the horizontal components of motion associated with a horizontally launched projectile, meaning a projectile with no initial vertical velocity. So that's important. I said that very slowly for a reason. If there's no initial vertical velocity, what does that mean? Initial vertical velocity. That means that initial vertical velocity, VIY, is equal to 0 meters per second. There's no initial vertical velocity. There's only a horizontal initial velocity for a horizontally launched projectile. If we angle it upward, then we'll have a VIY. But if we have only a horizontally launched projectile, we do not have a VIY. So let's think about the equations that we're going to use then for our horizontally launched projectiles, for determining the vertical components of our horizontally launched projectiles. So anywhere that we see this VIY, we can write 0. So for example, here, this would be 0. We erase that. So I'm just left with I'm going to scoot this over. VF final vertical velocity is equal to 2 times g, which is acceleration of the vertical, times y, vertical displacement. Then what about here? We have another one, VIY. Well, that's 0, so we can erase that. So here, we can move this guy over. So here's another equation. We have VFY, so final vertical velocity, is equal to acceleration due to gravity, which is g, times t, time. And then finally, in this one, erase some of this stuff here. You get the point. We have a VIY here. So this whole term gets erased. It's equal to 0. Okay, so we have 3 different kinematic equations here that we can use when we'll say up here, when VIY equals 0 meters per second, which is always going to be the case in our horizontally launched projectile. So let's put these equations, copy them, and put them over here. All right, so there we go. We have our horizontal components and our vertical components when we are talking about a horizontally launched projectile. A horizontally launched projectile has no initial vertical velocity, so we use these equations. We just get rid of any of the terms that contain VIY. Now let's look at what equations we need to use when we have an upward or angled projectile. So this is when we do have a VIY. So instead of getting rid of all of the terms with VIY, we're going to leave them in now. So that would look something like this. We have our horizontal components, so we're going to use the same equation as we did above. It's the exact same equation. Then we have our vertical components. Now we have parts of the same equation, but we also are going to leave in those components containing VIY because they're not equal to 0 anymore. So we have to leave them in. So these are the new parts of the equations. So you might be saying, why do I need so many equations? Why? I don't understand. Well, if you remember back to when we used our kinematic equations before, we're given different components of a problem. So for example, if I want to know let's say I want to know how long, so I want to know the time that it takes for an object that is launched with at an upward angle at a vertical velocity of 22 meters per second. I'm going to write this down so you can see it and not just listen. All right, there we go. So how long does it take? So that's t. I want to know t. For an object that's launched upward with an initial vertical velocity of 22. So this is VIY. This is the initial vertical velocity. To hit the ground, if its final velocity, and obviously I'm talking about vertical velocity because the horizontal velocity, 1, isn't mentioned, and 2, it's not going to change. Its final vertical velocity, so VFY, is equal to 61. So I'm not going to solve this problem. Let's just look at these 3 equations and think which equation could we use in order to solve for this. I know VIY, I know VFY, and I know AY because it's equal to G. Those are the 3 things that I know. So which equation has time? Which equation has time? That's where I should start because that's what I'm looking for. Well, very quickly I can see that the bottom one does not have time. This third one down here does not have time, so I can't use that one. I'm not going to cross these out because I'm going to use them again. Can't use this one. So I'm stuck with using this one or this one. So I have to look at all the things that I have. This has a VIY, so okay. This one has a VIY, okay. This one has an AY, good. This one has an AY, great. This one has a VFY. The first one does not have a VFY. I do not have a final velocity in that one. So therefore, I must use my second one. So this is the kind of problem solving you're going to need to be able to do. And then obviously you're going to have to be able to solve the problem. But you're going to need to be able to figure out which equation do I use. And first, so it's a multi-step process. It's not as simple as which equation do I use like it was before. Because you also have to determine, is this a drop? Which type of projectile is this? Is this a dropped projectile? Is this a projectile that's been launched horizontally, in which case I would use these equations? Or is it a projectile that is launched upward or at an angle, in which case I would use these equations? All right, so this is all of the information, but we're going to look at a really quick problem-solving strategy. So on the quiz, I will give you all of the equations. I will not give you this set of equations because you must understand that when VI equals 0 meters per second, we cancel it out from these 3 equations down here. So you need to be able to rewrite these 3 equations. You have to be able to rewrite them as these three equations, which is simple. You just take out the VIY components. But I will give you on the test, I'll give you this equation, I'll give you these equations, I'll give you the equations for solving final or total displacement, and for peak height. I'll give you all of those equations. I think you can look on the study guide. They're on the study guide that's posted on today's assignment. It's in the unit or the chapter 3.2 study guide. There's 1, 2, 3, 4, 5, 6, 7, 8 equations that I gave you. And I also give them to you. You know what? I'm going to... Okay, so I'm giving them to you like this. So you're going to be responsible for figuring out how to rewrite this. So you have to know that you have to replace D with either X or Y, depending on what you're solving. Depending on if you're solving for horizontal. Horizontal. You obviously are going to use X. If you're solving for the vertical components, that's spelled wrong, vertical, you're going to use Y. And then you're going to have to put in X or Y here, X or Y here. And then you're going to have to determine, am I looking at a horizontally launched? Oh my goodness. I'm calling this H launched, horizontally launched, or upward angled. If it's horizontally launched, remember we're not going to have our when we're finding the vertical component of motion, we're not going to have our we're going to have no VIY. There's no initial vertical velocity. So then we're going to have to cancel out all of our initial vertical velocities when we're solving for the vertical component. When we're solving for the horizontal component, we always have VIXT. That's going to be the same no matter what type of projectile we're looking at. So these are the three equations that I'm going to give you, and then you're going to have to determine how you correctly rewrite them, and then what components get canceled out based on what type of projectile you're using. So a problem-solving method, what I'm going to do is I'm going to give you, we're going to just do some example problems together, and we're going to learn the example problem, or the problem-solving strategy. I'll write it out right here, but then we're going to use the example problems to implement this problem-solving strategy. Alrighty, so here is a very basic outline. This is what you're going to do for every single problem, and if you do this, you're going to be successful. So first you're going to write down your knowns and your unknowns every single stinking time. Then you're going to convert everything into the correct units. You're going to determine the type of projectile, and then you're going to write out the equation or equations that you're going to need to solve. And I'm going to put a little asterisk here, and no, I'm not. No. Okay, anyway, you're going to write out your correct equations, and then you're going to solve. And sometimes when you solve, sometimes you may have to use the trigonometric method in order to complete your knowns and unknowns. To convert some of your unknowns into your knowns, because sometimes you're going to have more than one unknown. So remember for VIX and VIY, we may have to use trigonometric method in order to determine either of these two variables. So if I tell you that the initial velocity, if I don't specify the initial horizontal velocity, or if I don't specify the initial vertical velocity, if I just say the initial velocity, without specification, meaning without initial horizontal or initial vertical, this is a very big indicator that you're going to have to use that you'll need to use trigonometric method because the initial velocity, this is a resultant if it's upward, if it's an angled or upward projectile. Angled, there we go. All right, because if I throw an object up like this at a certain angle, if I'm standing here, and I throw the object, and I just say its initial velocity is 72 meters per second at 35 degrees north of east. So that 70, did I say 72 meters per second? 35 degrees. This is a resultant. So from this, I can determine VIX, and I can determine VIY, but I'm going to have to do the trigonometric method in order to do that. So just because it's just super important. I'm making a big deal out of this because it's going to make you lose so many points on the quiz and the test, the exam, if you don't understand this. If I say the initial velocity, you should understand that you're going to have to find VIX and VIY. Okay? If you don't understand what I'm saying right now, you need to make a note and you need to ask me, because you're going to really lose a lot of points for this if you don't understand or if you don't do it correctly. All right, let's look at some practice problems. I'm going to do two. Let's just pull them up here. Okay, so here we have our problem. It says a pool ball leaves a 0.6 meter high table with an initial horizontal velocity of 2.4 meters per second. Predict the time required for the pool ball to fall to the ground and the horizontal distance between the table's edge and the ball's landing location. So, according to our problem-solving strategy, first we're going to write down all of our knowns and our unknowns that we're looking for. So, let's begin with that. We have our knowns. So, the pool ball leaves a 0.60 meter high table. So this means that we have, if it's helpful for you, you can draw a picture. So we have a table, and the height of the table is 0.6 meters. 0.60 meters. This is the vertical displacement that the ball is going to fall. This is the height of the table. This is also the vertical displacement that the ball will fall. And this is y. Okay, so we have a high table with an initial horizontal velocity. So that's an initial velocity, and it's x because it's horizontal. It's 2.4 meters per second, an initial horizontal velocity. Let's write down our unknowns and our equations, but we're not going to fill those out yet. So let's just write down our unknowns now. So predict the time required. So we're looking for time for the pool ball to fall to the ground and the horizontal distance between the table's edge and the ball's landing location, aka how far out does the ball go? So if we look at our picture, if the ball's starting at the top and it gets thrown or hit off, the question says how far, or tell us the horizontal distance between the table's edge and the ball's landing location. So the table's edge and the ball's landing location would be x. So it's going to be very important that you can decipher these questions and pick out the pieces that are important that you're looking for. The variables, how they're named, how they're labeled, how they're described. Okay, so let's look at our equations that you'll have on your exam, or your quiz and your exam. So we're looking for time and we're looking for horizontal displacement. We should also add here that we know AX is equal to, not AX, AY, which is G, is equal to 9.8 meters per second squared. Do we know anything else? I don't believe we do. Okay, so we've written down everything, And now we need to make sure everything's in the correct units. Is everything in meters per second? Yes, we're good on that. So we don't have to convert anything. Now we're going to determine the type of projectile. So, is this a dropped projectile? No, it is not dropped. It's not a dropped or a thrown projectile, right? It's hit off of the table with only a horizontal velocity, an initial horizontal velocity. That means that it's not going upward. So that means we have a horizontally launched, and you can write it so you can remember, a horizontally launched projectile. All right, so if we're using a horizontally launched projectile, let's think about the equations that we have. So I'll go over these equations really quickly. That's our horizontal component of motion for any type of projectile. This is for a dropped object, or just how to find the vertical displacement. This is another one for the vertical displacement. This is T up. This is for determining the total time that the object is in flight. And then this one was for determining the peak height of the object. Then these are our three kinematic equations. So if I want to, what I would recommend you doing on your exam is just writing down, as soon as you get your quiz or your exam, write down all of these into their two different equations. That's not right. Write down these three into their three different vertical displacement or vertical equations. And then remember that this one is for the horizontal. Okay? All right. So since we are looking for horizontal distance, obviously we're going to have to use this equation, right? Because we're looking for x, so we're going to have to use that equation to solve for x. However, the problem is we know this, and we know that equation or that variable already, but we don't know time. That's another one of our variables that are unknowns. So what we're going to have to do is use some equation in order to solve for time first. So let's look at this equation. We have a y, we have a g, and we don't have a t, but we could rearrange this whole thing so that we could solve for t. So that is what we will do. We'll say y equals 1/2 a y t squared, or half g t squared, whatever one you want to use. All right, so now we have determined the type of projectile. We've written out our correct equations, so now we can go ahead and solve. All right, first we're going to rearrange this equation to solve for t. And when I do that, I get the square root of 2y divided by ay equals t. And so I can plug everything in here. T equals 2 times y, which is 2 times 0.60 meters, divided by ay, which is g, 9.8 meters per second squared. Take the square root of that, and time is equal to how many significant figures? We have 2 significant figures. 0.35 seconds. So now we know t. Erase all this. We know t. We can put it over here. 0.35 seconds. Get rid of our unknown t there. All right, now we're ready to solve for x. I'll do that in red. So horizontal displacement, how far horizontally does the ball travel? We have VIX, which is 2.4 meters per second, times time, which is 0.35 seconds. And we get x is equal to 0.84 meters. There we go. That one was pretty straightforward. All right, let's do another example here. All right, so here it says a long jumper leaves the ground with an initial velocity of 12 meters per second at an angle of 28 degrees above the horizontal. Immediately you should say, oh, this is a resultant. I'm going to have to do the trigonometric method in order to solve for VIX and VIY because I am not given those. I am given an initial velocity, which means the resultant velocity. All right, to determine the time of flight, the horizontal distance, and the peak height of the long jumper. Alrighty, this is a big one. Knowns, unknowns, and equations. So first, we know our resultant velocity. We're just going to call this VR. Is equal to 12 meters per second. Therefore, we must find VIX and VIY by doing the trigonometric method. And we'll say, we'll say 28 degrees above the horizontal. All right, so before we do anything, well, let's write everything we're looking for. So our unknowns, we want to know the time of flight. We want to know t. We want to know the horizontal distance, which is x. And we want to know the peak height of the long jumper. Remember, that is YP, peak height. All right, so before we do anything, let's do our vector resolution. So here, instead of, we're going to write vector resolution. I'm not going to make that a rule, but if it's got to be done, it should be done here, right after you've written down your knowns and unknowns. You should immediately do your vector resolution to find the component vectors. Okay, so we have a resultant vector that is 28 degrees above the horizontal, and it is 12 meters per second. So in order to find the horizontal component and the vertical component, VIY and VIX, we have to do this SOHCAHTOA. So, my jokes are so funny. All right, so let's do VIX, VIY. So is first opposite over hypotenuse. So the sine of 28 degrees is equal to the opposite, which is VIY, over the hypotenuse, which is 12 meters per second. Multiply both sides by 12. Plug it into the calculator. We find that VIY is equal to 5.6 meters per second. VIY, so the initial vertical velocity is 5.6 meters per second. Now let's do VIX. We're going to use cosine, COA, which is cosine of 28 is equal to the opposite. Whoops, I did that wrong, sorry. I wrote COA instead of CAH. It's not equal to the opposite, it's equal to the adjacent, which is VIX divided by 12 meters per second. Multiply both sides by 12, plug it into your calculator, and we find that the initial horizontal velocity is 11 meters per second. All right, so now that we've resolved that, we can write that up here. So we have 11 meters per second and 5.6 meters per second. Great. Now, also let's write AY, aka G, is equal to 9.8, what? Not 9.9, geez, 9.8 meters per second squared. All right, so one thing I want to point out really quick here, when you see the time of flight, you should immediately say, I'm going to have to use T up, I think, because remember that T up, remember that equation where we solve for how long it takes for the object to go from the start to the highest point? This is T up. And remember that the total time that it takes for the object to go back down to the ground, the total time is T. Remember, T equals 2 times T up. So if you see how long what is the time of flight, remember that you can use the t up equation to do that. So we need to know t, but we're going to have to know t up in order to solve for that. So remember, t up is equal to VIY times G, and that, we'll just say T is equal to 2 times T up. All right, so that one should be pretty easy to solve because we have everything. And then we have X. We know that X is equal to VIX times T. As soon as we have T, we can solve for X. And then we have YP. YP is this funky equation. YP equals VIY times T up plus 1/2 GT up squared. All right, so we're going to need to solve for all of those things. We're going to do that in this order also because we need time in order, or T up in order to solve for time. We need time in order to solve for X. Then we also need T up in order to solve for YP, or peak height. Okay, so let us begin. We're going to solve first for T up. T up is equal to VIY, which is 11 meters per second, times 9.8 meters per second squared. I have made a grave mistake, and hopefully this is what you do. I wrote multiplied by, but I meant divided by here and here. Hopefully you noticed that too. Divided by. This should be divided by. If you look at the equations, I just accidentally wrote multiplied by. Which is good because otherwise we have like 60 seconds of T up, which doesn't make any sense. So you should always be asking yourself, I know it's crazy. I think that's the second mistake. I think I made my first mistake ever in this class, and I just made my second mistake ever also in this class. It's fascinating. So you should be super careful to pay attention to, does your answer make sense? Because if you plug this in, you would have gotten 57 seconds. Does that make sense? For a long jumper to jump and to travel in the air for 57 seconds? No, that doesn't make any sense. So always be asking yourself, does my answer make sense? If it doesn't, check and see where you've gone wrong. So this makes a little more sense. 11, and did I write the wrong? Jeez, I'm on a roll. That's third mistake ever in my life. Oh my gosh. 5.6 meters per second. Sorry about that. Okay. 5.6 meters per second divided by 9.8 meters per second squared gives us 0.57 seconds. That is T up. So now I can move T up over here. 0.57 seconds. All right, now let's solve for time. Time is equal to 2 times T up, which is 0.57 seconds, which gives us 1.1 seconds. So total time is 1.1. Move this guy down. 1.1 seconds. T is equal to 1.1 seconds. You can just write it right here too if you want. All right, now for X. X, horizontal displacement, is equal to VIX times, I don't need to write VIX, do I? Is equal to 11 meters per second, which is VIX, times time, which is 1.1 seconds. This gives us a 12 meter horizontal displacement. And finally, we have our peak, YP, how high. So this long jumper is running, jumping into the air, and then landing, right? So he runs and jumps super far into the air, and then lands over here. So we just found that he travels 12 meters. We know that it takes him 1.1 seconds to jump from the second that he jumps off the ground until he lands. Now we want to know, what is the peak of his height? How high does he jump? So in order to do that, we have to plug in everything here. So we have VIY, which is 5.6 meters per second, times T up, which is 0.57 seconds, plus 1/2 G, which is the same as AY, so that's 9.8 meters per second squared, times t up again, which is 0.57 seconds, and that is squared. Oof. All right. So yp is equal to 4.8 meters is the peak height here. Oof. Okay. So there we go. We are finished. So in your homework, you're going to be in your practice problems, you're going to be asked to write your answer in a sentence. So you can't just write everything out like this. So look back at your unknowns. What were you looking for? I was looking for time. Okay, so let's write a sentence about time. The long jumper is in flight for 1.1 seconds. There's a sentence about the time that it takes, the time of flight of the jumper, 1.1 seconds. X, remember, X is the horizontal distance that the jumper goes. So the long jumper travels, 12 meters. 12 meters. Or you could say, let's not say travels. The jumper lands 12 meters from, we'll say 12 meters horizontally from where she jumped from. And the highest point, or aka the peak of the jumper's jump, was 4.8 meters. All right. This is how you give your answer in complete sentence form. All right, so some tips for while you're doing these practice problems. Be sure you follow this problem solving strategy. This is going to save your life. Second tip, when you're determining the type of the projectile, remember there are 3 types. There are dropped, even though I said we're not going to do a lot of those, you will still see at least one dropped projectile problem. So remember the equation that you need to use if you have a dropped projectile. We have dropped or we have thrown. All right. Then we have horizontally. There we go. So those are our 3. But just remember, be aware, you will see a dropped one. You've been warned. Don't forget that if you have to do vector resolution, you do it right here, right in the middle. And again, pay attention because you're going to also have to convert things on your practice problems. You will have to convert. So pay attention to that as well. All right, we are all done with lectures for this unit for physics, for high school physics. You're finished. So for high school science, you're all done. Wow, we made it through 4 years of lectures together. How exciting. That's beautiful. Aw. All right. So you have practice problems that are due on Wednesday. If you have any questions or you need help on the practice problems, please reach out to me via WhatsApp or Google Classroom comment. That is it. I know you're going to miss my voice so much. Let me know if you have questions. Have a good day off. Bye.